Okay, there are so many of these sort of problems at the end of this homework. I'm going to just do a few more because they're all sort of similar. So I'm going to right now actually work on number 33. So 33, give us this function. This is called a rational expression because it's like a fraction. They start out with asking, what's the domain of this function? So here we go, domain again. First, what is always going to be helpful when you have an expression like this is if it's not factored, to go and factor it if possible. And actually, this denominator is a trinomial, but it actually factors because if I multiply 11 times negative 10, it equals negative 110. But when I add those, it equals 1. So actually, this thing factors into x plus 11 times x minus 10. Because to find the domain, we need to have this denominator factored. So let's talk again about how we find domain. When we look for domain, all the possible values of x, our assumption is, to start with, the domain are all numbers. The only thing that's going to change that, there's only two reasons it's going to change. First is if you have any variables under a square root. Well, we have no square root in this expression. But the second thing that can happen, the second thing that can change the domain, is if you have variables in the denominator. And we do have variables in the denominator. The thing we have to do now is we have to decide what values of x would cause the denominator to be 0. And now, since we have these two parentheses, we realize if I look at the first parenthesis, x better not equal negative 11. And if I look at the second parenthesis, x better not equal 10. So if we look at our choices here, they do it, it's like set notation. Basically, we have two values that cannot be. Looks like it has to be b. Look at A. A has 0, 10, negative 11, 0. B is what we figured out. Now, question B says, what is the equation of the vertical asymptotes of r of x? Select the correct choice and fill in any. You know what's interesting? Up here, when we figure out the domain, when we figure out what x cannot be, those end up also being the vertical asymptotes. But sort of makes sense because I said before, vertical asymptotes are those dashed lines on the graph that the graph can never touch. And that's what we have here. Our graph can never be at x negative 11 or x 10 because the whole thing will explode. So once we find the domain and we find the exceptions by looking in the denominator, we also have the vertical asymptotes. So we would say we have two vertical asymptotes, x equals 10 and x equals negative 11. Which means, what that means is when you go get ready to graph this function, you go to 10 and you draw a dashed line, and you go to negative 11 and you draw a dashed line. So this is like a 10, this is like a negative 11. What is the equation of the horizontal or oblique asymptote? All right, we need to talk about, first of all, how do we find horizontal asymptotes of these rational expressions? All right, some of the stuff in order to do this we've talked about before. Let me write down this problem. Now to do the horizontal asymptotes, it's easiest, and I need to write the top and the bottom as polynomials, not factored, sort of in the unfactored form. So here's the unfactored form. The first thing I'm going to do, we talked about this before, reduce top and bottom to leading terms only. Remember I talked about leading terms? Leading terms means when you have a polynomial, it's the term with the largest exponent on the variable. Now here in the numerator, I only have one term, so that has to be the leading term. But if I look in the denominator, I have three terms. The leading term is going to be x squared. So really what I do is I sort of eliminate everything but the leading term. It's like I sort of ignore those, and I say basically you end up with x squared over x squared. Now to find horizontal asymptotes, this is a process you go through. You reduce the top and the bottom to leading terms, and then we compare. And three things can happen. And I'll give examples of each. Let's do this one first. The first thing can happen is, now I'm looking at the exponents. The exponents of the top and the bottom are equal. They're the same. Sometimes you have a problem. Say we had something like this. So this is our expression. We wanted to find the horizontal asymptotes, so we keep only the leading terms, end up with. So this is a case where I'll write it like the numerator, the exponent on the numerator is less than the exponent in the denominator, right? X cubed is less than x to the fourth. And then the last possibility, say you have something like this. You reduce it down to leading terms, which means you have 2x to the fifth over x squared. So this is when the numerator is actually larger than the denominator. So here we could have said the numerator equals the denominator in terms of the exponents on the variable. Let's do this one first. What happens if the numerator is bigger than the denominator? What happens to our horizontal asymptotes? Turns out you don't have any. If the numerator is bigger than the denominator, it does not flatten out. It just keeps going. How about if the numerator is less than the denominator? You have one horizontal asymptote, and we can tell you what it is. It's going to be y equals 0. If the numerator is less than the denominator, then you're going to have a horizontal asymptote, and on the graph it's going to be at y equals 0. Basically, it's like the x-axis. Now what happens if the exponents are equal? This is a little trickier. You have a horizontal asymptote equals the ratio of coefficients. In other words, here's the example. What's the coefficients for x squared on top and bottom? We don't really see it. It's actually 1. Ratio means the fraction of whatever numbers are in front of your variables. So for this example, horizontal asymptote would be y equals 1. Let's do a couple other examples. What if I had what if I was going to try and find horizontal asymptotes for this? You eliminate everything but the leading terms. So now we're at 3x squared over x squared. And now, since the top and bottom are the same, it's just the ratio. You can think of a 1 being here. And you would have a horizontal asymptote of y equals 3. How about if I had 4x squared minus 2 over negative 2x squared plus x plus 1. And I want to see what the horizontal asymptote is. You eliminate all but the leading terms, 4x squared over negative 2x squared. You notice that the exponents, the numerator and denominator, are the same. So what's the asymptote? It's just this ratio. All right, so that's all about horizontal asymptotes. So having gone over that, now let's go back to this one, because it said, what is the equation of the horizontal oblique asymptote? Actually, let's go back here. I should have said this. We're really talking about horizontal asymptotes, but when you have the numerator larger than the denominator, I said there's no horizontal asymptotes. But this is a case where there can be oblique asymptotes. In other words, when the numerator is larger than the denominator, there's no horizontal asymptotes, but there can be oblique asymptotes. So with that fact included now, for the problem we were working on, they're wanting to know, first of all, do I have any horizontal or oblique asymptotes, and what's the equation? Well, if I look up here, if I get rid of the leading terms, I have x squared over x squared. So that means you take the ratio, which is 1 over 1. It's a horizontal asymptote. So you end up with x squared over x squared. It's a horizontal asymptote, and it's y equals 1. You see that? Y equals 1. And now, based upon the stuff we just figured out, they give us 4 graphs, and they say, so which one is correct? And once again, you can just use process of elimination. It can be a little tricky, but here's what I would do. I would check what we call end behavior. End behavior. Let's see what happens large when x is a big positive number. Thinking about this, that actually might not. No, here's what's more helpful. Let's do this. You can see all these graphs have vertical asymptotes at 10 and negative 11. Let's see, easiest thing to do is, if I can increase this, look what happens. For A, when my x's are bigger than 10, it's saying we have positive numbers, and for B, positive numbers. For C, positive. For D, negative numbers. Let's see what happens. For instance, let's plug in x equals 11, and let's see whether the function is positive or negative. So when I plug in 11 into this equation here, what happens? Well, 11 plus 11 is positive, 11 minus 10 is positive, 11 squared is positive. If I plug 11 in here, I have a positive number. That means this one cannot be right. Now let's compare these and see what the differences are. In other words, when I compare this one and this one, look in here between 0 and 10. This one says the number should be positive. This one says the number should be negative. Well, let's plug a number in and see which is correct. Let's do an easy number. Let's do actually, and looking at this, it didn't ask us, but is there an x or y intercept? Let's think about that. If I rewrite my equation, this is how you do this problem. You just sort of think out loud. You try and see what could help. Here was the original equation. If I look for the y-intercept, that means I set x equal to 0. I would have 0 over negative 110, which is 0. So there actually is a y-intercept, and it's at the origin. So my line is going to cross, it's going to touch the y-axis. And the only one that does that, or I can't really tell. I guess that doesn't help too much after all. That's how this is. So let's go in here, and I compare B and C. In between 0 and 10, C says you get a positive number, B says you have a negative. So let's choose like 9, and let's see which one of these is correct. If I plug in 9 into this equation, I get 9 squared, and all I care about is it positive or negative. And that's going to be 20 times negative 1. That is going to be a negative number. So you know what? C says it's positive. And you know what also? Look at A. A says it's positive also. So at this point, only B says I get a negative number when x is 9. So it has to be B. It's like process of elimination. All right, that can be a little tricky. All right, let's do one more. Let's do one with an oblique asymptote. Here we go. So the last one we're going to do is 34. Let's see what they ask us. Analyze the graph of the function. So here we are. First question, the domain of f of x. All we care about for the domain is the denominator. I don't care about the numerator. It doesn't matter. And what am I worried about? What value of x is going to cause the denominator to be 0? I know x cannot equal negative 11. So I go down here. The only one that fits is this one right here. Once again, the numerator does not affect the domain. Only look at the denominator. Because the thing we're worried about is if we ever have a 0 in the denominator. What's the next question? What is the equation of the vertical asymptotes of f of x? Vertical asymptotes come from the denominator. Whatever value of x would cause the denominator to be 0, that also becomes your vertical asymptote. So we have a vertical asymptote at x equals negative 11. So when we get ready to graph this, we should have a dashed line that goes through x equals negative 11. What is the equation of the horizontal oblique asymptote? All right, so now we have to reduce this down to leading terms. So I get rid of this and this and this, and I'm left with x squared over x. This says there's no horizontal asymptote, but there is going to be an oblique asymptote. Now, what is the oblique asymptote? So let's take a look at how do we calculate an oblique asymptote. It can be sort of involved. So let's go over here and let's rewrite the function. How do we figure out what the oblique asymptote is? X squared minus 11x minus 12 over x plus 11. We can rewrite it y equals x squared minus 11x minus 12. What you do is, to figure out the oblique asymptote, it's like we're going to do sort of like old-fashioned division. You know, you could think of a fraction as a division. 4 over 2 is the same thing as 4 divided by 2. So we're going to think of this as x squared minus 11x minus 12 divided by x plus 11. Matter of fact, what we're going to do is we're going to use and actually go in and do a really old-fashioned division problem, sort of like a long division. So we're dividing by x plus 11, so inside goes x squared minus 11x minus 12. All right, this is a little different, but it's sort of like when you divided numbers, long division years ago. What I do is I really only care about this first term here, the x. And I'm looking at x squared, and I say, what do I need to multiply by x to equal x squared? Well, obviously, x. And now I do it. So I multiply x times x, which is x squared, and then x times 11, 11x. And then I subtract this whole thing. X squared minus x squared is 0. Negative 11x minus 11x. It's actually negative 22x. And then I bring down this term. And now I say, what times x would equal negative 22x? It would be negative 22. Negative 22 times x is negative 22x. Negative 22 times 11 is I guess I have to get out my calculator. Hope I'm not making any math errors. We're going to find out. 22 times 11, negative 242. So I'm going to subtract this. Negative 22 plus 22 is 0. Negative 12 plus 242 is like plus. So what we're saying is, when we do old-fashioned division, what I've just discovered is this whole thing, I could say, is x minus 22. And this is like my remainder, plus 230 over x plus 11. So when I divide it, I get the main part here, and then I get the remainder. But what happens is, when you think about end behavior, if I think about what happens when like x gets to be a large number, since I've got an x in this denominator, it sort of like goes away. And what happens is, I end up with an asymptote, and this is going to be like a diagonal line. It's not a horizontal line, it's not a vertical line, it's diagonal. And it's y equals x minus 22. So that's what they're asking for. They're saying, what's the horizontal or oblique? Well, it's not horizontal, but it is oblique. And the equation is y equals x minus 22. And now they want us to graph it. So we go here. So basically, you see this, all four of these graphs have this dashed line here. So that's my oblique asymptote. Now I just have to see which one of these is correct. You can see also I've got the vertical asymptote of x minus 11. So the key is, what's going on? So first of all, if I look here, for minus 11 on, the graph is saying they're all positive here. Here they're negative, positive, and negative. Well, let's just see. Matter of fact, let's make it easy. Let's see what happens when x is 0. So let's rewrite my when I plug in x equals 0, what do I get? Minus 12 over 11. That is a negative number. So therefore, when x is 0, well, it's actually a little hard to see here. I guess I can't assume. I can't tell what happens there. So maybe 0 wasn't a good choice. How about a better choice might be, if this is negative, let's say when x is negative 10. What happens when x is negative 10? So you get negative 10 squared minus 11 times negative 10 minus 12 over minus 10 plus 11. So this is a positive number. This is a positive number. This is like 100, 110. This whole thing's going to be positive, the top, and this is positive down here. It's going to be a positive number when x is minus 10. So this one could be correct. This one's definitely not correct. This one could be correct. This one's not correct. So now I'm down to B or D. So what's the differences? We'll see, look at D. Here it's like this, and here it's way down here. The difference is maybe like when x is minus 12. So let's see what happens when x is minus 12. Because this one says when x is minus 12, I'm going to get a positive number. This one says it's going to be negative. Well, let's see which one's correct. So you have minus 12 squared minus 11 times minus 12 over minus 12 plus 11. So once again, this whole thing is going to be positive. The top, the bottom is negative, positive by negative. This whole thing is going to be a negative number. So definitely it has to be B. All right. That was a little crazy, but that's what's involved with these graphs. Sometimes it's just trial and error, trying to figure things out. All right, so that concludes doing almost all the problems from this homework and looking over all those, and almost every question on the test should look like something that we've done in these videos.